Start. Hello and welcome back to Calculus 3, section 11.2, vectors in 3D. So we are going to upgrade the dimension, but in terms of theory, we're not picking anything up technically. You want to have the understanding of dimensions. I already talked about that briefly, but I'm going to draw some pictures now, make hopefully more sense. When you have a number line or just the line, we call that one dimension, so that will be 1D, and it's just length. If you have two dimensions like this, which is creating the area, that will be 2D. Talk about the area. And this one is just going to be one variable. This one is two variables, x and y. Then we can create a cube. That would be 3D. Talk about the volume. We'll hear about this a lot. And the coordinate system, there are a few ways we can draw. That's the focus of this lecture. So let's use the right-handed x, y, z for most part. And then you can go up in dimensions as far as you want. We can draw the tesseract, the hypercube, but we don't have to, whatever, here, since I am already there. I missed that one. And then there are the inner ones that also connect on the other side. So that will be the 4D bulk, and then that would have a four-dimensional, right, system, which is not as easy to draw. So there will be x, y, z, let's say w. This one is just x, y, z. This one is x, y, and this is just x. So these are some of the things that we need to understand. And I already said this before. Your number of dimensions is simply the number of variables that you introduce in your point. And those points are locations in space that could be on any of these dimensions. So now we want to focus on 3D. Most of the Calculus 3 is in 3D. Say 90% of it. We draw the coordinate system. This is one of the ways. And we label it x, y, z. Now, these are only positive axes. You have this axis go forever into negative x, right, way, and then negative y and negative z. So they would go forever. But we just draw the first octet because these axes would create planes which cut the space in 8 regions. So if you only have x and a y, they cut the entire 2D realm into 4 quadrants, right? 4 parts. But if you are to build the wall, the middle of the classroom, and then in the middle of the classroom, and then put in a floor in the middle of the classroom, another level, you would have 8 rooms. So in 3D, you don't have quadrants, you have octets. There are 8 of them. When you take planes and you intersect them at the single point. We call the point in the middle origin, again, and that point is 0, 0, 0. and all axes that go through that origin are perpendicular to each other. So we have 90 degrees between all three, any pair of the three axes that we have. We still have x, y, and z axis there. Now, this coordinate system is called right-handed coordinate system. And the reason is you will wrap your hand around the z-axis, and since it's a right-handed coordinate system, when you start bending fingers, tip of the fingers will first go through x-axis and then y-axis. That's why it's called the right-handed. You also have the, so this is the right-hand coordinate system. You can also draw this way, and some of you, if you use AutoCAD, you can switch these things. Now, with the left hand, as your thumb is pointing towards the positive z-axis, as you wrap your fingers around z, your tip of the fingers first touch x. So that's the rule. Tip of the fingers as you wrap around, so you have to have thumb pointing up towards the z, the positive z. And then when you wrap your fingers around, what is the axis that you hit first? If you hit x-axis first as you wrap with whatever hand, then it's that hand system. If you hit y, it's the other hand system. So as you can see over here for the left hand system, if I wrap around, the first axis I'm going to hit is y, and then I'm going to hit x. So that's why right hand would be wrong for this. Therefore, it's the left-handed. Over there, if I use the right hand and wrap around, I first get to x-axis and then to y. I hope you visually can imagine that actually the xy is the floor, and then z is 90 degrees up. So this is the left-hand system.
What happens if you tip it so that z is on the floor?
You don't. That's the best answer I could give.
Okay.
Now,
Are these all positive as well? Like these are
all positive, just positive half of the axis, yes.
for both the left hand and right?
Mm-hmm.
Okay.
Now, there's another way to draw these systems, and that is to intersect like this and say this is x, this is y, and this is z. Still, you have right, left, and all of that stuff. So sometimes it's easier for us to see graphs and stuff when we use the isometric view, right? So that will be it. Now over here you can see the negative y, the negative x, and obviously if you extend down, negative z axis. So that's also one of the ways. And it might be easier for you to see that right here is the plane that's the floor. So at any point in this class, if you're having issues visualizing something, you should immediately look at the space around you, because you can place the 0, 0 in the corner over there, in the floor, and then the x-axis would be the one with the door, the y-axis would be the one with the board, and the z-axis is the corner that goes up. 0, 0 in the corner, and you can quickly see that the floor is xy plane. Now that floor xy plane is your good old 2D xy plane that you used so far in mathematics, right, from your elementary algebra through Calc 2. All of the functions you used to draw are actually a piece of chalk and draw it on the floor. All right, that will be your sine x and cosine x and ln x and everything else, x squared plus 3, whatever you come up with. Those are here. So if I want to draw sine x, I would just go like that. That's sine x. And then this would be 2 pi over here, and right here would be 1 and negative 1. So those are the values that we...
Did you know 2 pi upside down?
Yes, I have.
Oh, gosh. Very visually advanced to you.
All right. So now we are going to graph a point. In 3D space, our point is going to be determined by 3 coordinates, x, y, and z. And to draw this, let's say the point is, so graph 3, 4, 5, obviously very creative. We will get to 3 first on x-axis. Then we would have 1, 2, 3, 4, right, to come up with a point in 2D. So observe that this is one-dimensional, just 3 on x-axis. Now this one over here is 3, 4 because we drew this one on the floor. And now we have to go 5 units up. So this point over here is 3, 4, 5. So what was the way to draw this? We go down the x-axis, parallel to the y, parallel to the z up, and we reach the destination, which was 3, 4, 5. Now, if I want to look at the xy plane alone, the xy graph for this particular picture would be 1, 2, 3 on x, 1, 2, 3, 4 on y, and that's 3, 4. So this is just the floor. Now it's very important to connect what you see here with what I have in the blue and a corner. Because when we work with three-dimensional functions, your domain is no longer going to be on the x-axis from negative infinity to positive infinity. Your domain is going to have all kinds of weird shapes as regions on xy plane. Because to determine z, you will have to have x and a y, and that comes from the 2D region. So your domain will be two-dimensional. So you have to get used to having a two-dimensional domain, but luckily, you just need to look down to the floor. That's your domain, right? And the z would be what y used to be, right? The value of the function, the range. So now that we know how to graph functions, right? Now that we know how to graph functions, oh, by the way, one more thing that I wanted to point out here, guys. The z-axis will be at the origin, shooting out of the paper or the screen or so on. So the paper, right, the value would be going this way, in this case, towards you. And if this was 3 units and that's 4 units, then it would be 5 units. So the point is somewhere over here, right? Actually.
Thank you.
All done? So now we know how to see and distinguish which one is which. We know there are 8 octets. The point is x, y, z. Now when I have points defined, I can stretch the vector between 2 points. So if the point P is A, B, C, and the point Q is, I don't know, X, Y, Z, whatever. No, let's do the LMN. I will do the terminal minus initial point, so PQ vector in 3D, right? It will be L minus A, M minus B, N minus C. I have my spiky brackets for vector notation. I have the vector above PQ to denote that that's a vector as well. And we know that the PQ and QP are not the same vector, right? The QP vector would be negative of PQ, and it would be A minus L, B minus M, and C minus N, telling us that PQ is negative QP. They have the same magnitude. The direction is 180 degrees off. Now, we know that vectors have magnitude and direction. Well, direction is not as easy to deal with in 3D. So we are going to see some ways of positioning later on during the class as the course progresses, but right now we actually are not defining anything for the direction. We just say if you have vector u with components u1, u2, u3, because it's a 3D vector, we say the magnitude of vector u is going to be square root of u1 squared plus u2 squared plus u3 squared. That would be magnitude. Now, we do have those special unit vectors we talked about. The general case is vector u hat is any vector u divided by its magnitude. So this formula, which we learned the last class, works in any dimension, so it works in 3D as well. But we also have those vectors that give us the x, y, and z direction. So we have I hat, which is 1, 0, 0, j hat, which is 0, 1, 0, and k hat, which is 0, 0, 1. So these are the three vectors which allow us to write that vector u, which we could have as, I don't know, a, b, c, let's say. We can write that as ai hat plus bj hat plus ck hat. So we can use either one of the two notations. All of the properties which we covered in 2D translate, right? So properties from 2D vectors transfer here, because those properties are not just for 2D or 3D vectors. Those are just property of any dimensional vectors. It doesn't matter. So all of the properties still hold the same. Addition of vector, scaling vectors, so let's put that as well. Addition or subtraction of vectors is component-wise. So it's done component-wise, is done component-wise, and then scaling of the vector is done by C times u. So these are all ideas that we have from before. So now let's quickly define u as 1, negative 2, and 7, and vector v as 3, 3, and negative 5. And let's figure out what is 2u minus v equal to. Right, so we have 2 times the vector 1, negative 2, 7, minus the vector 3, 3, negative 5. So we have, when we scale the first vector, we get 2, negative 4, 14, minus the vector 3, 3, negative 5. So 2 minus 3 is negative 1. Negative 4 minus 3 is negative 7. 14 minus minus 5 is 19. Right? Minus and minus gives plus. So the answer for this is negative 1, negative 7, and 19. That will be the vector.
It would mean I, J, K.
You can also write it as negative I hat minus 7j hat plus 19k hat. Sure. So you can do that as well. Okay, so what's next? Next is to take a look at a few other formulas that are not necessarily vectors, but I don't know, they're in this section for some reason, so let's take a look at those. So what do we have? First one is the distance formula in 3D. Maybe I should, let's put them. So distance formula in 3D. And the formula is going to be the same as your 2D formula, except you are going to add one more dimension. So the distance will be the square root of, and now it's the distance between 2 points, so we have x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Square root of the whole thing. That will be the distance formula in 3D. Now if you have 2 points and they are connected with a straight line, in the non-curved space you can find the midpoint, right, on the straight line by using the midpoint formula. In 3D. Again, it is the simple average of coordinates for each one that I mentioned previously. So it's a point, so we use the parenthesis. We have x2 minus x1 x1 plus x2 divided by, so x1 plus x2 divided by 2, y1 plus y2 divided by 2, and z1 plus z2 divided by 2 as a point. Again, it's a point, so we use the parentheses, and it's a 3D point. What else? equation of the sphere, right? I'm not going to say in 3D because sphere is a ball and that's a third-dimensional object. Two-dimensional analog is circle, but that's flat and that's on the right on XY plane. So I'm just going to say sphere. I'll actually put ball, right, in parentheses. And the sphere can be centered at 0, or it could have a center away from the origin. So I'll write two equations. One is x squared plus y squared plus z squared is equal to rho square. So we can use rho as radius. So rho, radius. Greek letter rho. And then the center for this is at 0, 0, 0. Right? It's centered at the origin. Now, if you want to have a sphere that it's not at the origin, you will have to come up with x minus a squared plus y minus b squared plus z minus c squared equals rho squared. In this case, center is at ABC, whatever those values are. So we can figure out the sphere that way. Good. And can also talk about basic plane. So basic planes. When I draw the coordinate system, each pair of axes will create a plane. Now I need you to pause for a second and look at the room around you. I told you that we are going to place 0, 0 coordinate system, right, the origin, at the corner on the bottom. That makes the line that goes along the wall and the floor towards the door the positive x-axis, right? Because if you do the right coordinate system around the z pointing up, you have to hit x first and then y. Y goes along the board, z goes up. You see that x-axis, which is going towards the door on the floor, and the y-axis that it's on the floor going alongside the board, is creating a plane, and that plane is the floor. So the floor is actually your good old xy plane. So I can just draw in over here, right, a plane and this plane is xy plane. Let me just see how far they, because we have two lectures. This is actually discussed in 3 separate lectures, but one of them is tangent planes, and we'll deal with that. I just need to see how far we go in this section. So, okay. The next one will be x and z. So this plane over here is xz plane, and oh, maybe well, I'll add stuff. Leave space to the right, because I'll be adding things as soon as I draw all three. Because I need parallel planes, we'll do that as well. So I have the what is this, xz plane, and then one more, and then I'll go back and fill in more stuff. X, Y, Z, and we have now, oops, X, Y. So if you put the top lines to be perpendicular with with the y-axis, then it should be easy. There we go. So this is a YZ plane. Now we're going back. I have XY plane over here, and this XY plane is the floor. And this one, since it's floor, it's happening where the Z is equal to 0. So this particular one is Z equals 0. Guys, that's the floor that we walk on. If you look up, the ceiling, which is, say, 10 feet high, is going to be another plane that is parallel to the one that we have, and that one is at whatever the height, in case, let's call it 10 feet, is going to be at Z equals to 10. So I can draw another plane, right, on the top, right, and that other plane, if it's going through number 10, that other plane is going to be called Z equals 10. Now observe, it's a XY plane, but it's labeled Z equals. You've seen this concept before with vertical and horizontal lines. I'm going to draw something and then erase. In the XY coordinate plane, right, the 2D, you had a concept of the vertical line. This vertical line was parallel to y-axis, but its equation was x equals to, let's say, 3 in this case. Right? So it went through number 3, and that's why the equation is x equals to 3. Similarly, for your horizontal line, which was parallel to x-axis, it will be called, because let's say it goes through 2, it's called y equals to 2. So horizontal line and the vertical line had equations y equals to 2, x equals to 3, well, x or y equal to a number. So now these basic planes, like the floor and the ceiling and the 4 walls around us, are all going to have basic equations. Floor is equal to 0, and the ceiling is equals to 10. On the next floor, if there is one more floor above us, well, that ceiling would be Z equals to 20. Because if this one is 10, then another one, 10 again, so 10 plus 10 is 20, Z equals 20. And let's say there is a basement underneath this, it will be Z equals negative 10, presuming that it's the same height, whatever the height of the basement is. So now, when I look at XZ plane, which is the wall on which we have the door, opposite to that wall is another, so that one is actually going to be called Y equals 0. So let's make sure that that's also Clear? So the basic one is y equal to 0. Now we have this one that it's parallel to it. Now how far is this? Exactly how far it is.
I mean, it looks like it's a little bit of a double.
Just, I need exact number. How far is it exactly?
Should we pace it out?
You don't need to, just count it. Oh yeah.
What do we count?
Well, but there's
Four tiles?
But there's no tiles over there.
Yeah.
Tiles, yeah.
And there's like 30 tiles.
So yeah, you count
So
the tiles.
ceiling
Each tile is 2.
like 2 feet.
2 feet,
probably.
and then
So
times the number of tiles. It's very simple.
5, 6. There's about like 7.5. So 7.5 times
But
2.
there's like a little one
29.
over there on that side.
So 29 feet.
All right, so 32. Great. So, well, yeah, you have the little bit over there, and then you have those.
Oh yeah, I just did half. Oh, we had the other half. It'd be 29.5 for half of the room. So that times 2.
Something went wrong.
50.
Exactly.
58. 59. So total 59 feet,
No,
I think.
I'm going 28 feet.
Unless I counted wrong.
So 16 tiles times 2, I was right, 32. 32 feet.
Surely.
I don't know what I heard.
So, what is the equation of the
Wait, no,
window
you're
wall?
tiles. I was
It is going to be y equals 32. So if I have another wall parallel to this one, I will draw, let's say, I will draw here, and that one is at 32. The second plane is y equals 32. Book has a little bit better drawing for this. So here, you can enjoy this for about 17 seconds. So you see the last picture, the green picture, replace that 3 with 10 and you have your floor and your ceiling. Then the middle one are going to be the door wall and the window wall, 32 feet apart, so y equals 0 and y equals 32. And then the other way, that's longer, so let's call it 40. You have x equals 0 on this wall and x equals 40 on the other wall. When you put those planes together, they confine the box, right? They create the box and we are in that box. So the space in which we have this class is very well defined with just basic equation of the plane. Now we are going to have another lecture where we are going to slant these planes and then we are going to create, you know, the, let's say, roof and other cool stuff. Thank you.
Yeah.
Yes, cool stuff. Exactly.
Cool with a K.
Mm-hmm. Is there anything else?
The cool stuff. His last name.
Yeah, believe it or not, that covers the section. Yeah, I hope you're not disappointed, but... All right, so let's practice some of the stuff. How about some of the problems from the book to make this more interesting? Exactly. What is the equation of the sphere? With center 0, -2, and 6, with the point with the point 1, 4, 8 on the boundary. So what is the equation of the sphere with the center at 0, -2, 6, with the point 148 at the boundary. Go. What do you have to find first? Radius. How would you find the radius?
Formula.
So the distance x minus a between the center and the point along the boundary.
Good. So it's the distance formula between the center of the ball and the boundary. Good. So you will use distance formula to figure out the radius. Once you have the radius, you just plug everything into the formula for the sphere. You have the center, you have the radius, just plug numbers in and we're done.
Yeah.
Obviously.
Okay. Seems that you guys are done, which is nice. So what's the radius? Radius is going to be the square root of, and now we have 1 minus 0 squared. That's distance between x's, right? Plus 4 plus 2 squared plus 8 minus 6 squared. I have a square root of 1 plus 36 plus 4. That's 41? Perfect. So radius is square root of 41. Well, not our concern because it's going to get squared, right? It's rho squared, so it's 41 at the end. So what do I have? I have x minus the center, which is x minus 0. So that's just x squared. Plus y minus 2, so that's y plus 2 squared, plus z minus 6 squared, equals to square root of 41 squared, so it's just 41. And that's the answer. That's the equation of the sphere. You're gonna love this problem. I have 10 of these problems. No, we're just going to do one, and then you can enjoy the other 9 at home. Find the equation of the sphere. X squared minus 4x plus y squared plus 6y plus z squared plus 14 equal to 0. Yeah, but let's see the standard form. Because you don't really know the center or radius. You just know it's a sphere. Because you see positive x squared, positive y squared, positive z squared. So yeah, it's a sphere. But what's the center? I should ask what is the center and what is the radius. But I can also say find the equation of the sphere, because you just get to read those values off of it. How would you do that?
Yeah, factor out some.
Nope. Nope. Completing the square. Very good. Hello, intermediate algebra. So long ago, right? For some of you, algebra 1. You might never take an intermediate.
What you know?
So. What was the completing the square?
I don't know. I subtract the 6.
Yeah, add and subtract. Yes, yes. So you pick up the b term, right? The middle term. So you pick up b, you cut it in half, you square it, and that's the magic number you add and subtract. Nice. So we see these are those b terms. There is now one for z, so z squared we don't have to complete. That's just done. All right, so we have groups to worry about. Only 2 groups to worry about. B value is -4. So -4 divided by 2 squared is 4. And over here b is equal to 6. So 6 divided by 2 squared is 9. Those are the values that we add and subtract to complete the square. So the first parenthesis is x squared minus 4x. Let me use different color. Plus 4 minus 4. Plus y squared plus 6y, and then we have plus 9 minus 9, and then we have plus z squared plus 14 equal to 0. So now complete the square. So the first 3 will give us the x squared. So square root of the first, sine of the second, square root of the third, squared. And then we have minus 4. That's a leftover. Plus, again, completing the square, square root of the first, sine of the second, square root of the third. And then we have minus 9. Plus z squared plus 14 equal to 0. Now we have x minus 2 squared plus y plus 3 squared plus z squared is equal to, oh wait, -1?
Yeah.
The hell? Yeah, we just fixed the problem. Now this 14 magically becomes 17. Yeah, I update the problem right away, so yeah, it becomes 17. And then the answer over here is 4.
Negative 4.
You have to make numbers smaller as well.
Oh, yeah, I have to make smaller. So 10 is good, right? And then it's 4. Right?
Yeah.
No, it's not. This is 13. I have to make it 9.
Oh, God.
Yes. Born and raised. So we change this number to 9 so we can get the 4 at the end. Perfect. So this is modified problem 38. It's 38 with the correction. So it's actually doable. The other way, you can't have it negative on the other side, right? Okay. Radius cannot be negative, right?
What if you split it the other way?
No. Let me spell it out. N-O. So we have the center at 2, negative 3, 0, and radius rho is 2. Ta-da! So completing the square, if you have issue with that, we are going to use completing the square when we do conics again. So make sure you are okay with the linear term is the one that has b in front, and then b is negative 4. Cut it in half and square it. The linear term again is the one in front of the y to the first power. That's the linear term. That's where b is. You're remembering, I don't know if you're remembering, but you should be remembering this. So that's why it's called b. It's front of linear term where x or y or z has the exponent 1. That's where b is. Anyway, so that's that. And where would we be if we don't introduce some physics into all this, which is actually statics at the same time? So an object, so we immediately draw the elephant, right? There we go.
Oh, man.
So the object is acted with two forces. So force F1 is 1063, and the force F2 is 049. What is the force 3 so that the object stays in equilibrium, i.e. is not moving anywhere, as all three forces are acting on it? Nice. So the unknown force will have three components, A, B, C. We are supposed to add the three forces. So sum of all forces needs to be equal to 0. That's the concept. So we are going to take the force 10, 6, 3. Add to it the force 0, 4, 9. Add to it the force ABC to get the 0 vector, which is 0, 0, 0. We don't want any resultant force out of all of this. So now we know that we are supposed to add all of the x components. That gives us one equation. 10 plus 0 plus a equals to 0. From where a is negative 10. 6 plus 4 plus b equals to 0, from where b is negative 10. And 3 plus 9 plus c equals to 0, from where c is negative 12. So your force 3 that we need to counter all the other forces is -10, -10, -12. They did not give us units, so I will put newtons. And let's leave it at that. Ooh. They have cool problems too. Look at that. Put like 4 of these on the test, we're good. So, you have an object that is suspended by 4 cables. It's very simple to imagine, right? Have 4 cables on the ceiling supporting one object. You can see that. Now, each one of those cables will have tension, which is the force. And that's these red lines. This thing is pulling down with the weight, or whatever the weight is.
Gravity.
The mass times gravity is the weight.
Okay.
So now, you have the points, the coordinates of the points, and you can calculate the vectors and figure out, so 4 cable load of 500 pounds, so that's the force that it's pulling directly down. Load hangs from the 4 cables equal length that are anchored at the points, and they give you the points. And the load is located at this point. Find the vectors describing the forces of the cables. Well, you have the coordinates, so you just do the vector components in between. Right? It's the PQ deal when you subtract the coordinates to find the vectors. Right? And then, since everything is symmetric, and all of the ropes, the cables, are the same length, they all share the equal amount of load on them, right, in terms of the force they're supporting. And they have to support all 500 of the weight that is given. So it's a very interesting problem. You should look at this stuff, and this is what the engineering is all about. There is one above with 3 cables and so on. So, look into these things. They're interesting. And your project is something along these kind of lines, some applied problems and things. Well, that concludes this lecture. We're going to take 5 minutes and then be back with 11.3, the dot product.